So the first thing that I want to say about proof is that no proof springs forth onto the page fully formed and perfect, right? Almost every proof in mathematics starts out as a sketch. And the folklore is that there are a million great proofs in math, and they all started as sketches on the back of a bar napkin while sitting over cocktails, right? That's actually more true than you might think. So one of the things I'm going to always encourage you to do anytime you're working on writing a proof is write a napkin version first, your sort of scribbles, right? Just getting stuff onto the page, playing around with it, it doesn't have to look good the first time that you write it down. It's when that napkin version, so when you find the discovery that you need to find, and then you need to actually translate that into a written proof, that's the translation step that I want us to be most thinking about right now. So as I look at some of the proofs that your groups have handed in so far, some of them sort of take more of a paragraph narrative form that's written down here. Some of them have very few words and mostly formulas and symbols written down. So what I would say is that the one that has very few words probably looks like maybe your bar napkin version of a proof. You made the algebraic discovery that you needed, but you haven't turned it into a written piece of communication yet. So that just sort of shows the different spectrums, the different place on this evolution that those proofs might be right now. And the four things I'm going to ask us together to look at in these proofs are, first of all, the structure and strategy. So Spade's group, this is the one that you're going to be looking at. An effective proof, if I'm reading an effective proof, I should be able to understand what is the strategy of proof that's being used here. I should be able to identify, is this a direct proof? Is it an indirect proof? Is it a contradiction proof? If it is a contradiction, where is the contradiction? What is it contradicting? If it's an induction argument, what is the nature of the induction? If it's an argument by cases, where are the cases? One of the things that really helps to make a structure or a strategy evident is cutting up your proof into, not making your paragraphs too long, maybe is another way to say that, right? One or two sentences, white space. One or two sentences, white space. That way, where you do have multiple cases or you do have other things, you're sort of clearly identifying what those things are up front. So Spade's group, when you read through the proofs, you're going to be looking at them with an eye towards how clear is the structure and the strategy that this author is using. How clearly does that emerge in the writing? Second piece, and this is one that I harp on a lot, and that's burden of proof. In an effective proof, we should always know as a reader, what do I need to see in order to know that this proof has been successful, right? What is the standard of proof? What evidence is the author trying to demonstrate to me that once I see it, I will know the author has been successful? So burden of proof often comes in the form of statements like, we will show, or we must show that, ... So very often, a burden of proof will be stated very early in a proof. So Diamond's group, this is the one you're going to be thinking a lot about. But then, often what happens over the course of a proof is that burden will shift. As you maybe use theorems or use definitions or do something else to kind of change the state of play, you may need to say, we will show that kind of statement, maybe multiple times, as what you're trying to show changes and shifts a little bit. So, but the reader should always know, what is it that I need to see next that will show that this proof is done? Like, what is the burden of proof this author is trying to meet? Number 3 is one that novice proofwriters always struggle with until you take a computer programming class. And once you take a computer programming class, that's a great place to break you of the habit that leads to this not working out so well. That's the no surprise symbols dictum. Anytime you use a symbol, like a variable or a set or something, before you use it, you have to tell the reader what it is, where it comes from. If there was a quantifier that brought it into existence, eliminate that quantifier. These are often done by what I call let statements. So don't do anything with x until you first say something like, let x be. Very much, proof authors can get almost like a godlike complex in writing a proof, right? Because what are you doing? You're bringing x into existence as part of your proof. Let there be x. And then tell me what x is. Where did it come from? Was there a quantifier that got eliminated? Whatever. And then only after you've said that can you start using x. So put that let statement up front so that the reader knows, okay, now there's an x on the stage in front of me. Here's where it came from. Here are the properties that I know it's going to have. And then now we can do some calculations with it. So the key test here is anytime you see a letter, like an X or something in a proof, look north and ask yourself, has the author defined this X first? You might even just cover up the bottom part of the proof and say, there better be something above here that tells me what X was before it was used. So let statements. And then finally is attribution. This is like the mathematician's version of what English professors call citation, right? That any time that you're making a deduction, you should be telling the reader should know why that deduction is valid. Make references to the authority of other established results and claims, things that the reader already believes. You're not going to get the reader to believe something new unless you, first of all, remind them what they already believe, and then demonstrate to them why they must, therefore, believe the next thing as you're leading them down the path toward your ultimate result. Right? And so where we have let statements, we also have bylines. I call them bylines. These are statements like, by definition of blah, 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 by construction, by assumption, by theorem 2.7, right? Making those references to provide authority to the validity of the deductions that you're making is crucial, because that also helps the reader to make all the connections between the different ways in which the theories and the previous results and the ways that you brought variables into existence or whatever in your proof, the way that those all come together to make the proof bigger than the sum of its parts, right? So these are the four things that I'm going to have us look at in today's proof clinic. So each of your groups assessed the same set of 5 proofs on one of these 4 different dimensions. And what do you notice about these rankings, if anything? Is there a story that this data is telling you? So the highest ranked on each of these 4 dimensions is up here on the left. The lowest ranked is over here on the right. What do you see, Kenzie? There's a lot of variance, exactly. So what's the take home from that? No, I don't think so. The variance, right? Yeah. We all have room to grow in different areas, right? Great proofs can be great in any number of different ways. And in the same way, ineffective proofs can be ineffective for any number of different reasons, right? And so I think one of the things that I like about this exercise is it shows you where maybe your proofs are already good in some of these categories, and maybe other categories are the ones that you need to work more on. I'm particularly interested in what happened between the first 3 of these dimensions and the 4th. There's almost a complete reversal in the proofs that were rated more highly and the proofs that weren't rated as highly. The proofs that didn't do these 3 as effectively did attribute their authority of their claims the best. So I think that's really fascinating. So what I want to do, actually, to close things out is just to look at one more proof together that we'll just sort of do as a large group, with an eye towards these 4 things to figure out how we can write that proof effectively. So here's the result that I want us to think about. Actually, the group that was working on left and right cancellation in our last class, or no, maybe it was the unique inverses group. Unique inverses group wanted to use a property that I call mixed cancellation. They said, well, can't we just use, if I have this equation, xy equals zx in a group, can't I just use right cancellation to get rid of this x, and then left cancellation to get rid of that x, and conclude that y is equal to z? And I sort of was hesitant at the time. And the reason I was hesitant is as follows. Here's a theorem, that if it's true that mixed cancellation is a thing in a group, then G needs to be an, okay, this might be the first time we're using this word, abelian group. Anyone know what abelian means? It's a fancy word for a property we already know. It's the commutative property. Yes, exactly. Abelian is just a fancy name for a group whose operation satisfies the commutative property. So what is a commutative property again? I.e., what would the commutative property say for the group G? Yeah.
A times B times C is equal to C times, or yeah, A times B is equal to C.
Yeah. A, B is equal to BA, but your group was the group that just did the no surprise symbols thing, and yet you've given me some surprise symbols. A and B, what in the world, where do those come from? For which A and B does that need to be true? All A and B taken from what set?
G.
Yes. There we go. Cool. So that then is the proposition. So in particular, what this means is that mixed cancellation is only a thing in the case where the commutative property holds in our group. So let's see if we can first come up with the napkin version of this proof, and then begin the process of thinking about those 4 elements of effective proof communication, see if we can come up with a way to write it out. So let me grab where'd my napkin go? Well, all right, maybe I'll just write the word napkin over here in the corner. It's kind of lame, but whatever. All right, napkin. So in my napkin proof, what am I trying to do? I'm assuming that this statement here is true. I'm trying to deduce that the red statement is true for all A and B. AB is equal to BA. So maybe I'll just on my napkin write XY equals ZX. And then this is true for all XYZ. For all XYZ. We know that this is true. And what I want to prove, maybe I'll write down at the bottom of my napkin, want to prove that for all A and B, that I have AB equals BA. And so first of all, let me ask you this question. What is my burden of proof right now? What is the statement which, if I prove it, if I deduce it, then we're done? Say again?
Y equals Z?
Well, not quite. So, oh yeah, I'm sorry. I didn't finish this thought up here. Mixed cancellation says that xy equals zx implies y equals z. And what's the role of this mixed cancellation in my theorem I'm trying to prove? What's the, maybe backing up a step, what is the logical form of this assertion that I'm trying to prove? It's got an if, and it's got a then. Right? If G is a group that satisfies this orange property, then G is a group that satisfies this red property. Right? If G is orange, then G is red. So I guess we don't know what our burden of proof is until we decide on a strategy for our proof. What's an example of a strategy we could use to prove an if orange, then red statement? What are some options? Maybe a contrapositive. So we could say, assume that G is not abelian. Then we will deduce that G does not satisfy mixed cancellation. That would be a contrapositive approach to the proof. What would be another example?
A direct proof of just saying if orange is true and then prove that.
If orange is true, well, the if doesn't give me anything to work with, but what I would do is actually maybe even assume. But yeah, so if we did the direct proof, we would just assume that the orange statement is true, and then try and deduce that the red statement is true. If that's my method of proof, then in my actual proof, I would probably say so. I think direct proof is probably the more straightforward approach for this one, just because both the orange and the red properties give me an affirmative statement. Like, for all x, y, and z, this thing is true. For all a and b, this thing is true. And negating those can make affirmative statements a little more complicated. It's a lot harder to work with a not equal to sign, especially in abstract algebra, but even generally. So I think I favor the direct approach. So if I wanted to signal to the reader that we're going to use a direct proof, what should my first line be? I think Kenzie already said it. Assume, and what am I assuming?
Assume G is a group that satisfies the mixed cancellation.
Yes. Assume G satisfies mixed cancellation. And now how would I then signal to the reader what my burden of proof is? What must I then show? We wish to prove what?
That G is an abelian group.
Yes. We wish to prove that G is abelian. That's my burden of proof now. Right? And the fact that I've assumed the hypothesis and then stated the conclusion as my burden of proof signals to the reader that this is a direct proof. Right? I'm going to kind of put a little BOP here. Burden of proof. We wish to prove G is abelian. Okay, so what would it look like to prove that G is abelian? By definition of abelian, we have to prove this statement. For all A and B in the group, AB is equal to BA. So I want to bring an A and a B into existence here. But I can't do that by just writing A and B. What do I have to do first?
Let there be.
Let there be. Yeah, we need a let statement. So let A and B, where are they coming from?
Elements of G.
They're coming from G, so I have to say that. And how are they being chosen? Am I choosing them? Or is the cosmic whim of the universe choosing them?
For all.
Because there's a for all up there, it's not us specifically choosing them. It's the cosmic whims of fate choosing them, right? We have no control over which A and B land on the stage in this proof. So usually we convey that by saying chosen arbitrarily. So that's called eliminating the universal quantifier, if you like the really fancy logical term for it. It's what happens when a for all statement gets invoked to create new material for my proof. A and B are now in existence. We know they came from G, and we know that we, as the authors, had no control over which A and B got chosen. They were chosen by the universe because there's a for all statement up there. Okay, so now that's my let statement. Now there's no surprise symbols. What's my new burden of proof? Now that I have an A and a B on the stage, what do we wish to prove?
A, B is equal to B.
Yeah, exactly. So that's what I meant earlier when I was talking about shifting the burden of proof. So we had an original burden of proof statement. We wish to prove G is abelian. But then to actually make that operationalizable, I don't even know if that's a word, to actually make that an actionable part of our proof, we had to let the universe choose A and B for us, and then restate to the reader, okay, now that I have an A and a B, as soon as I prove AB is equal to BA, we're done. Because that is the definition of abelian. So now from here, it's just a way, it's a matter of trying to figure out how to use this mixed cancellation property to make this deduction. And in the interest of time, what I'd like to do is finish this thought on my own time and post this video up in our channel afterwards.